So in this video, we're going to cover how to use MATLAB to implement Euler's method and solve a differential equation using Euler's method in MATLAB. And this is part 2 of Introduction to Solving Differential Equations Numerically. So the differential equation that we're going to try and solve in MATLAB should be our old friend, the logistic equation. dy dt is equal to a growth term that we call k times y times 1 minus y all over the carrying capacity c. And that, of course, comes with an initial condition. Y at time 0 is equal to y0. This is our initial launching point, of course. So if we're going to iterate forward in time, we're going to start at that value of y0 and just march forward incrementally. Before I get ahead of myself, I just want to remind us there are 2 parameters in this model, k and c, so we should go ahead and define those if we're trying to solve this numerically, so we can actually go ahead and iterate, since just unknown parameters or undefined parameters in a model like this, when we solve things numerically, we're not going to be able to actually find more iterations or more time steps. So let's just give some of these parameters values. Let's say k is equal to 0.75. Let's say c is equal to 100. And let's just give an initial value of y0 is equal to, let's just go with 15. And of course, these are really just to get us started, so we can start actually implementing this algorithm and starting to test it out. And the recipe that we used, again, is coming from Euler's method. So from the previous video, the recipe we derived really was from using the definition of derivative and basically approximating a limit, just saying we had some delta t that was small enough. So I'll just throw the recipe back up here. We had y at the next point in the future, that is the current time, plus a little bit of time in the future, delta t. Well, that's equal to the previous time step value of y, or just y at time t, plus the incremental time step, delta t, that small value that we're jumping forward in time, all times the original right-hand side of our differential equation, f of y. So again, the way in which we think about Euler's method is that we're sitting at some value of y at time t. If we just add to it delta t times that right-hand side function evaluated at y of t. So actually, let's just go ahead and write that in. That is really f of y of t. And we add that to the previous value. We then get the next value of our solution, the next approximate value of our solution, I should say. So for our specific example here, the right-hand side is given by that logistic derivative up above. So this is our function f of y. So let's just go ahead and rewrite our Euler's method in terms of that right-hand function, right-hand side function, just so we're on the same page. So we have the next approximation in our solution at t plus delta t is equal to the current solution value or the previous solution value at y of t plus our little time step delta t times that right-hand side function, which is k times our solution at time t, all times 1 minus our solution at that current or previous time t, all over that carrying capacity c term. So I just want to emphasize in this case that we're evaluating all these y's on the right-hand side at the current value t. And then we're getting the next value of our solution at t plus delta t from it. So in a very kind of an abstract sense, this feels very much like a discrete dynamical system, where we're using the previous or the current value to get to the next value of the solution. So the iterations will feel somewhat familiar to what we've already been doing. So let's go ahead and start trying to implement this on a computer using MATLAB. So inside of MATLAB, I'm going to be in whatever folder I want. So here, just my math bio folder. I'm going to go up to new script, click new script, to bring up a blank function, or a blank script, excuse me. And I'm going to write this as a function so I can call it from that command window in MATLAB. And let's just call this Euler's Logistic. A very clever name that just suggests, hey, we're using Euler's method to solve the logistic equation. I'm going to go ahead and save it just so I don't lose my work. So a few things that we need to do ahead of time, just like we did for solving discrete dynamical systems, is we first need to start defining parameters. So I'll use all my comments, kind of break up code to make it a little more readable. In this problem, we have two parameters, k and c. So I'll just go ahead and define those. K is 0.75, and I said this is, our growth term, or growth rate. And we also had C, and I said that was what, 100? And that was our carrying capacity. All right, the next thing we should probably discuss is just defining that initial condition, or that initial value. So we can go ahead and implement that. So I'll just copy some of this comment stuff. And I'm going to call this initial value. So we had our initial value was set at 15. And now similarly to just what we did for discrete dynamical systems, we're going to want to save all of our solutions in a vector. All of our solution time points, if you will, in a vector. So if we have some initial value, y0, we want this to be the first value in our solution. Say our solution is, I'll call this y solution, and that'll be the first value in there. Okay. So I'll say y sol of 1 is just equal to our initial value. I'll say store initial value in solution vector. So all of our solution values are going to go into y sol. The next thing we need to discuss for differential equations now was that time step aspect. This time step, of course, tells us how far we're moving forward in time. So delta t, 2 delta t, 3 delta t, and so on. So we're imagining our solution, increasing or changing as we move forward in time. And of course, we're only getting the solution value at those specific points of delta t, 2 delta t, 3 delta t, until we keep going delta t's into the future. And we're literally just jumping forward in time. Now, the kind of difference here between discrete dynamical systems and our Euler's method and differential equations is the number of delta t's we want. We just need to make sure that we are iterating enough to get to a final desired time. So for example, if delta t is 0.1 and we want to get to a final time of 2, we need to do about 20 iterations. Since it's 0.1, 0.2, 0.3, all the way to 1.6, 1.7, 1.8, 1.9, then finally 2. So the way in which we'll do this, we're actually, as a heads up, going to use a while loop, just to say, hey, while time is less than our final time, keep iterating. But either way, I'm getting a little ahead of myself. Let's define that time step and call it dt, and let's set that as something small while we use 0.01. And the other time information we can do is our final time, and let's set that at, I don't know, let's say 10 for now. And I'll say this is our final simulation time. So if you do the math out here, if we're just bouncing or iterating or stepping forward in time by 0.01, so we'll get 0.01, 0.02, 0.03, 0.04, and we're going all the way to a final time of 10, that's going to be a lot of iterations. So let's actually go ahead and try to start this iterative process. And to do that, we need to start our initial time at 0. So I'll just say initialize time to 0. And this, of course, should match where our initial value is. So in this case, I'll just be clear and say our initial value was at t equals 0. If our initial value started at t equals 3, we would need to reassess what's in line 18 here. And what we want to say is to use a while loop to just keep marching forward in time. And the way in which we'll use a while loop is basically to say, hey, while the time that we're at in the simulation is less than or equal to, or let's say less than, t final. We want to keep going ahead in time using our recipe that we came up with over here. And I'm just going to go ahead and write an end to just close that while loop. So the way in which we want to step forward in time is we're going to need one other aspect, because if we're solving our solution and storing it in that y solve vector, we need to know what index we're at in terms of the solution or the value in that vector. So for example, this point here would be y sol at 1, or y sol at 2, excuse me. This would be y sol at 3, and so on. Y sol in 4. So we need to keep changing that index the more and more solutions that we put in. So we need a counting variable of some sort. So I'm just going to write something and make this a counter. So that's just a counter to help us out as we go through that while loop. And if we want the next solution, let's go ahead and just bring this to the next page. And let's write this step out all together. So if we want the solution y sol at 2, we know that this is going to be equal to y sol at 1 plus delta t times k times y sol at 1, the previous value again, all times 1 minus y sol at 1 all over c. So this is how we get y sol at 2. Y sol at 3 would be similar. So what we can really envision here is, well, if this is my counter, what I actually need over here is counter plus 1. Oops. Since in line 23 up here, we initialize this to counter, so we can go ahead and kind of use this, but generalize this step for any time step that we want. So we can have y solution at counter plus 1 is equal to y solution at counter plus our time step dt. And we're just going to then have to write in that right-hand side function of our differential equation. So this will be k, that parameter we already defined up above in line 6, times y sol at 1, and then times that big parenthesis, where we have 1 minus, oops, that y sol at 1 should actually be y sol of count, excuse me, because we want that previous value like we discussed here. And then we have 1 minus y sol of count all over c. So let me just drag this open so we can see that entire line. And that is our differential equation getting solved to the next time point. Now, I'm just going to write that this is our Euler step here, or Euler's time step, because that's how we're getting more and more solutions using Euler's method. But there's a few things that we basically need to make sure that we're doing. We need to update the counter in time, because so far we just said, hey, whenever time is less than time final, just keep doing this. And well, we initialize time to be 0. So right now time is less than t final because t final is 10. So we're just going to keep doing that, but we've never actually updated what time is. So we need to say time is equal to time plus dt. The next thing we should do is also update our counter, because as it stands right now, counter is just equal to 1. So even every time we go through this for loop, or this while loop, excuse me, count is always just equal to 1. So we're just going to store things in y of 2. And y of 2 will be equal to our Euler step evaluated at y of 1. So once we do this, we should have our solution and everything should update accordingly. And remember, from a computer science standpoint or a computer programming standpoint, when we have something like t equals t plus delta t, the computer always reads left to right. So it's not thinking the equivalence works the other direction from right to left. So we're really setting the value of t as whatever's on that right-hand side. We're always, in this case, setting the value of ct, our counter, in terms of whatever is on the right-hand side. So we have our solution now. Hopefully, we haven't tested it yet, but let's go ahead and try to plot it. And this can be a little difficult because, well, we have our solution, y of sol, but we don't actually have our time values. So what we can do in this case is one of two things. And what I would recommend is we just store our time in a vector as well. So up here, where we initialize time at 0, we can say this is tvec of 1 is equal to 0. And I'll say store first time value. And every time we throw a t plus delta t, we'll just store that new time in our solution value as well. So down here, we can update the counter in time, and we can also store the next time point. So tvec of count plus 1 is just equal to t plus delta t. Again, we're just trying to store a vector of times at the same times that we've stored solutions. This is basically just turning into a counting problem. We want to have the same amount of time saved as we have solution points. So now we have our solution in two vectors. We have the time vector, and we have the associated solution at all of those times stored in the time vector. So let's go ahead and try to plot this. Just using a standard old plot command. I'll try and jazz this up by just making the markers a little larger, just so it's a little easier for all of us to see. And let's go ahead and try to run this code. This was called Euler's Logistic. And there is our solution. And of course, we could add axes labels. We can add a few other bells and whistles to make this plot a little more interpretable. And I'm just going to go ahead and do that for good measure. So we can add our X label, that's just time. We could add our Y label, that is our solution, y of t. And the other thing we can do is change the font size to make them larger. So we can do set, what's called GSA, add our attribute font size, and say font size of 22. There's a little more easier to read graph, and of course we could change the axis size and things like that as well. But I hope this gives you an idea of how to solve differential equations using Euler's method in MATLAB.